What if everything we think we know about human progress is missing crucial chapters? Picture this: 2,000 years ago, an intricate bronze device with interlocking gears could predict solar eclipses and planetary movements with pinpoint accuracy. Centuries before modern medicine, surgeons performed cataract operations with tools we'd recognize today. And long before the age of skyscrapers, builders mixed a special concrete that didn't just endure for decades, but for millennia. These aren't myths or lucky guesses. They're fragments of a forgotten past where ancient civilizations achieved breakthroughs that vanished from history, only to be rediscovered centuries later. The truth is, our ancestors were far more advanced than we've ever given them credit for. Somewhere along the way, wars, natural disasters, or simply the passage of time erased knowledge so sophisticated it rivals our modern science. Think about that for a moment. Entire systems of understanding engineering, astronomy, medicine developed independently across the globe, then slipped through the cracks of history. What could explain these gaps? Were these ideas too far ahead of their time, or were they deliberately concealed? And most haunting of all, how many more secrets are still waiting to be found? That's exactly what we're about to explore. Over the next 22 revelations, we'll journey through the most astonishing lost knowledge systems ever documented. From the Viking navigators who used crystals to steer through fog, to the Inca's knotted cords that may hold untold stories, to the Byzantine flamethrower that science still can't replicate, each discovery challenges our assumptions about human innovation. These aren't just curiosities, they're proof that brilliance isn't confined to any one era. So if you've ever wondered how much of history remains hidden, or what ancient wisdom could teach us today, you're about to see history in a whole new light. The past is far stranger and far more ingenious than we've been taught. Buried beneath the waves off the Greek island of Antikythera for over 2,000 years, a corroded lump of bronze and would lay waiting to rewrite history. When sponge divers stumbled upon it in 1901, they had no idea they'd uncovered what scientists now call the most sophisticated mechanical device of the ancient world. The Antikythera Mechanism wasn't just a simple clock or calendar. It was an intricate cosmic calculator with over 30 interlocking bronze gears, each precisely cut by hand to track the movements of the sun, moon, and planets. Turn its crank and dials would display upcoming solar eclipses, the timing of Olympic Games, even the irregular orbit of the moon with an accuracy that wouldn't be matched until the invention of modern mechanical clocks in the 1800s. What's truly baffling isn't just the mechanism's complexity, but the historical context in which it was built. This wasn't created during the height of Rome's empire or the Renaissance. It dates back to between 150 and 100 BC, a time when most of Europe was still using primitive tools. The device's differential gear, a component essential for calculating celestial motions, was thought to have been invented in the 16th century until researchers realized the Greeks had perfected it millennia earlier. Fragments of inscriptions on the mechanism suggest it might have been linked to the school of Posidonius, a philosopher who studied the heavens, raising the possibility that this was just one of many such devices, perhaps part of a broader tradition of ancient Greek engineering now lost to time. Modern X-ray scans reveal just how advanced the craftsmanship was. Tiny teeth on the gears measure barely a millimeter across, yet they mesh together with precision that would challenge even today's engineers. Some researchers believe the mechanism could simulate the irregular wobble of the moon's orbit, a subtlety only observable with precise astronomical records. This implies the Greeks didn't just understand mechanics, they possessed observational data refined over generations, possibly inherited from even earlier Babylonian astronomers. The real mystery isn't how it worked, but why this technology vanished. No other devices like it have ever been found from the ancient world. Was the Antikythera Mechanism a unique masterpiece, or did wars, fires, or the collapse of classical civilizations erase an entire lineage of mechanical knowledge? Some speculate that devices like it were kept secret by elite scholars, while others suggest the materials were melted down for weapons or coins over centuries. Whatever the case, its rediscovery forces us to reconsider what ancient civilizations were truly capable of, and how much brilliance might still lie hidden beneath layers of time. In the hands of a medieval warrior, a blade forged from Damascus steel wasn't just a weapon, it was a masterpiece of metallurgy that could slice through lesser swords like parchment. These legendary blades, produced between the 3rd and 17th centuries across the Middle East, bore mesmerizing wavy patterns resembling flowing water, a visual signature of their extraordinary strength and flexibility. What made them truly remarkable wasn't just their beauty, but their performance. Historical accounts describe these swords bending 90 degrees without breaking, holding razor-sharp edges through countless battles, and even cleanly cutting a silk scarf dropped onto their blades, a feat modern replicas struggle to achieve. The secret lay in the steel itself. Unlike ordinary iron, Damascus steel was crafted from woots, a high-carbon alloy imported from India and Sri Lanka. Ancient blacksmiths heated and folded this material repeatedly, not just to remove impurities, but to create microscopic structures called carbon nanotubes, a discovery that stunned scientists when they examined the blades under electron microscopes in the 21st century. These nanotube fibers, stronger than anything produced in medieval Europe, gave the steel its legendary resilience and sharpness, even more baffling. The process by which these nanostructures formed remains a mystery. Modern attempts to recreate Damascus steel using historical descriptions often fall short, producing blades with similar patterns but lacking the original's unparalleled performance. Some researchers believe the key might lie in trace elements present in the original Wootz ingots, possibly from specific mines long since depleted. Others speculate that the quenching process, where red-hot blades were rapidly cooled, involved unique organic materials like plant extracts or even urine, altering the metal's crystalline structure. There's also the possibility that the slow, controlled cooling of the steel in the forge allowed these nanostructures to form naturally, a technique modern industry, focused on speed and scale, has overlooked. The loss of this knowledge wasn't accidental. As warfare evolved and gunpowder reshaped battlefields, the demand for these labor-intensive blades dwindled. The last masters of the craft took their techniques to the grave, and the mines supplying the crucial Wootz ore were eventually exhausted. Today, what we call Damascus steel is often pattern-welded imitation, a homage to the original's artistry but not its substance. The genuine article represents more than a lost manufacturing technique. It's a reminder that some ancient innovations emerged from a deep, almost intuitive understanding of materials that modern science is still piecing together. Perhaps the most humbling lesson of Damascus steel isn't just that we've failed to replicate it, but that its creators achieved such precision without microscopes or metallurgical theory. Their knowledge was empirical, passed down through generations of trial and observation, yet it yielded results that continue to elude our high-tech labs. In a world obsessed with progress, these blades whisper an uncomfortable truth sometimes. The past holds secrets we haven't yet earned the right to rediscover. Picture this scene from the 7th century. Byzantine ships surrounded by enemy fleets in the waters of Constantinople, outnumbered and desperate. Then, with a terrifying hiss, jets of liquid fire erupt from bronze tubes mounted on their decks, flames that cling to wooden hulls, spread across the water's surface, and refuse to be extinguished even by waves crashing over them. This was Greek fire, the Byzantine Empire's most closely guarded weapon and one of history's most formidable military secrets. For centuries, this incendiary terror gave Constantinople's navy an unstoppable advantage, burning through invading fleets and saving the empire from collapse time and again. What made Greek fire so extraordinary wasn't just its destructive power, but the sophisticated science behind it. Contemporary accounts describe a sticky, gelatinous substance that ignited upon contact with water, a property that defies conventional chemistry. Some reports suggest it could only be extinguished with sand, vinegar, or urine, hinting at a complex mixture of ingredients. The delivery system was equally advanced, pressurized nozzles called siphons, possibly using early pump technology, allowed operators to spray the flaming liquid in continuous streams like ancient flamethrowers. This combination of chemical innovation and mechanical engineering suggests a level of technical knowledge far beyond what medieval Europe possessed. The secrecy surrounding Greek fire rivals modern classified weapons programs. Only a handful of artisans and the imperial family knew its formula, with legend claiming the Emperor Constantine Roman IV had the knowledge split among multiple experts to prevent any single person from recreating it. When enemies captured Byzantine ships equipped with siphons, they found the mechanisms deliberately smashed beyond recognition. Even the name, Greek fire, was a misdirection. Historians believe it may have contained petroleum from the Black Sea region, mixed with quicklime, sulfur, or pine resin to create its signature adhesive flames. Some researchers speculate that naphtha, a volatile byproduct of crude oil distillation, formed its base, while others point to undocumented additives that gave it unique combustion properties. What's most striking is how this technology vanished. After the fall of Constantinople in 1253, the formula disappeared completely, not just from practice but from written records. Modern attempts to recreate Greek fire using historical clues produce flammable mixtures, but none match the terrifying descriptions of a substance that burned on water and couldn't be quenched. This raises profound questions. Did the Byzantines stumble upon a chemical reaction we've yet to rediscover? Or was their formula dependent on rare materials now lost to time? Beyond its military impact, Greek fire represents a paradox of human progress. Its development shows how conflict can accelerate innovation, pushing civilizations to explore chemistry and engineering under dire necessity. Yet its disappearance also reveals how fragile knowledge can be when guarded too closely, a warning echoed in other lost technologies. The flames that once protected an empire now illuminate a different truth. That advancement isn't guaranteed, and some discoveries, once extinguished, may never blaze again. In a dimly lit vault at Yale University lies one of history's most perplexing puzzles, a 240-page book filled with looping, alien script and illustrations of plants that don't seem to exist. The Voynich Manuscript, named after the Polish book dealer who acquired it in 1912, has resisted every attempt at decipherment for over 600 years. Its pages are a riot of contradictions, delicate herbal drawings alongside naked women bathing in green liquid, astrological charts peppered with unfamiliar constellations, and paragraphs of text that follow grammatical patterns yet remain utterly meaningless to modern linguists. Carbon dating places its vellum pages between 1404 and 1438, but the origin and purpose of this enigmatic book remain shrouded in mystery. What makes the Voynich Manuscript so uniquely frustrating isn't just its undeciphered text, it's the tantalizing hints of system hidden beneath the surface. Statistical analysis reveals its writing follows Zipf's law, a linguistic principle where frequently used words appear in predictable patterns, just like real languages. Yet despite decades of effort by cryptographers, including World War II codebreakers and artificial intelligence algorithms, not a single word has been conclusively translated. Some theories suggest it's an elaborate cipher, perhaps an early attempt at secret communication by Renaissance alchemists. Others propose it's a constructed language or even a glossolalia, a stream of unconscious symbols with no fixed meaning. The most unsettling possibility, that it represents a completely lost linguistic tradition, a way of encoding knowledge we no longer possess the keys to understand. The illustrations deepen the intrigue. Botanists have failed to match most of its 337 plant drawings to any known species, leading some to speculate they're encrypted representations of real herbs or fantastical inventions. One section depicts intricate cosmological diagrams with radiating circles resembling cellular structures or microscopic views centuries before the invention of the microscope. Another shows tiny human figures interacting with what appear to be interconnected tubes or vessels, sparking wild theories about proto-scientific knowledge of anatomy or even early concepts of energy flow. Modern technology has only added layers to the mystery. Multispectral imaging has uncovered faint, erased text beneath some pages, suggesting the manuscript might be a palimpsest, a recycled book with older writing scraped away. But even these ghostly traces defy interpretation. In 2019, a study claimed the text shared similarities with ancient Hebrew when processed through an algorithmic cipher, but the hypothesis collapsed under peer review. Another team suggested it could be a form of Proto-Romance language, yet no consistent translation has emerged. Perhaps the most compelling clue lies in the manuscript's very persistence. Over the centuries, it passed through the hands of Holy Roman emperors, Jesuit scholars, and rare book collectors, all captivated but ultimately defeated by its secrets. The fact that no one ever came forward to claim authorship or explain its contents suggests either an extraordinary secret worth dying for, or a hoax so meticulously crafted that it fooled generations. Yet the labor involved, quill-written text on costly vellum, intricate illustrations in multiple pigments, makes a mere prank seem unlikely. The Voynich Manuscript forces us to confront the limits of our historical knowledge. In an age where information seems permanent and accessible, here's a tangible reminder that entire systems of thought can vanish without a trace. Whether it's an encrypted herbal manual, an alien artifact, or the deliberate creation of a medieval eccentric, its very existence whispers a humbling truth. There are still pages in humanity's story we haven't learned to read. High in the Andes, where the Inca Empire once stretched across thousands of miles without a conventional writing system, an extraordinary alternative emerged, not carved in stone or painted on parchment, but woven into colorful cords of knotted strings. Quipus, often mistaken as simple accounting tools, reveal a sophistication that modern scholars are only beginning to unravel. Each quipu consists of a primary cord dangling subsidiary strings in a cascade of intricate knots, their positions, colors, and types forming a complex language of information. For centuries, historians dismissed them as basic tallying devices, recording crop yields or population counts. But recent breakthroughs suggest these textile artifacts may hold something far more profound. Entire narratives, histories, and even philosophies encoded in fibrous code. The real revelation came when researchers noticed quipus weren't uniform. They varied dramatically in structure, not patterns, and even the direction of twists in the chords. Some strings bore clusters of knots resembling mathematical place values, consistent with the Inca's advanced decimal system. Others defied numerical logic entirely, with asymmetrical arrangements and color combinations hinting at symbolic meaning. In 2017, a team studying quipus from the Peruvian village of San Juan de Colota discovered two specimens that local elders identified as narrative documents, letters between village leaders during 18th century rebellions. If verified, this would confirm what oral traditions have long claimed, that quipus could convey detailed messages as rich as any written text. Deciphering them, however, remains a monumental challenge. Without a Rosetta Stone, a bilingual key to cross-reference, each discovery raises more questions than answers. Spanish chroniclers noted that Inca administrators, called quipucamayos, could read the chords aloud like scribes reciting from a book, suggesting standardized conventions lost to colonial suppression. Some scholars propose the knots represent syllables or logograms, while others believe their arrangement mimics the spatial logic of Andean landscapes, mapping information vertically like the empire's terraced mountains. The colors derived from natural dyes might indicate categories: yellow for gold, red for soldiers, or white for peace, but their full lexicon remains elusive. What's most revolutionary about quipus isn't just their complexity, but what they imply about the Inca worldview. In a society without alphabetic writing, three-dimensional thinking thrived. Information wasn't flattened onto pages but organized in tactile, relational structures where meaning could be felt as much as seen. This challenges the Eurocentric assumption that advanced cultures must develop script. The Inca built the largest pre-Columbian empire in the Americas, with sprawling roads and precise stonework, all administered through a system that modern databases might envy. Yet their primary medium was fiber, not ink. The tragedy is how much was destroyed. Spanish conquistadors, intent on erasing indigenous knowledge, burned countless quipus as idolatrous objects. Today, only about 600 survive, many scattered in museums where their original context is lost. But new technologies offer hope. Digital modeling allows researchers to analyze knot distributions at scale, while collaborations with Quechua communities, descendants of the Inca, are reviving oral traditions that might hold interpretive keys. Quipus force us to reconsider what it means to write. In an age drowning in digital data, these tactile records whisper an alternative, that knowledge can be tied, twisted, and dyed into existence. They remind us that innovation isn't bound by linear progress sometimes. The most brilliant systems are the ones we're still learning to see. Standing beneath the dome of Rome's Pantheon, it's easy to forget you're looking at a 2,000-year-old ceiling, one that hasn't needed major repairs since Emperor Hadrian's engineers poured it in 126 AD. While modern bridges and sidewalks crumble after 50 years, Roman concrete structures defy time, enduring earthquakes, wars, and even seawater with uncanny resilience. The secret to their longevity wasn't lost magic, but a brilliantly simple ingredient: volcanic ash. Recent studies reveal that the Romans mixed their concrete with a special volcanic powder called pozzolana, which triggered a chemical reaction giving their structures self-healing properties. When tiny cracks form, rainwater reacting with the ash forms new mineral deposits that seal the gaps, a regenerative process modern scientists are only now beginning to replicate. What's astonishing isn't just the material's durability, but how deliberately the Romans engineered it. Analysis of harbor walls in ancient Austria shows they used different concrete formulas for different environments, changing the mix of volcanic ash, lime, and crushed rock based on whether the structure was submerged, load-bearing, or exposed to weather. Maritime concrete, for example, contained a specific type of volcanic glass that reacted with seawater to grow stronger over centuries. This wasn't accidental chemistry. Roman engineers like Vitruvius wrote detailed manuals specifying which quarries produced the best materials, demonstrating a systematic understanding of material science that rivals modern civil engineering. The disappearance of this technology is as puzzling as its effectiveness. After Rome's fall, medieval builders reverted to weaker mortar recipes, and the knowledge of pozzolana concrete faded until the 18th century. Some historians speculate that the centralized Roman economy collapsed the supply chains needed to transport volcanic ash across Europe. Others suggest the labor-intensive mixing process requiring precise ratios and meticulous curing proved too complex for smaller medieval workforces. There's also evidence that later builders misinterpreted Roman texts, focusing on the lime content while overlooking the critical volcanic additives. Modern researchers have spent years reverse engineering these ancient formulas. In 2023, a team at MIT discovered that the Romans' use of hot mixing combining lime and ash at high temperatures created calcium-rich lime clasts that act as built-in repair kits. When water seeps into microcracks, these clasts dissolve and recrystallize, mimicking the way bones heal. This revelation could revolutionize sustainable construction, potentially reducing the cement industry's massive carbon footprint by extending infrastructure lifespans exponentially. Roman concrete forces us to rethink the myth of inevitable progress. Here was a material so advanced that it degraded less in 2 millennia than modern equivalents do in decades, yet its secrets lay dormant for centuries. Perhaps the real lesson isn't just about chemistry, but about how easily knowledge can fracture when societies collapse. The Pantheon's unyielding dome stands not just as a marvel of engineering, but as a silent challenge. How many other solutions to modern problems might be hidden in plain sight, waiting to be rediscovered? Long before the sterile operating rooms of modern hospitals, ancient Indian healers performed delicate surgeries with tools crafted from bamboo, bone, and even the jagged edges of seashells. The Sushruta Samhita, a medical text dating back to 600 BC, describes procedures so sophisticated they wouldn't become standard in Europe until the 19th century, from reconstructing noses amputated as punishment to removing cataracts with curved needles. What's most startling isn't just the existence of these techniques, but the systematic way they were taught. Sushruta's text outlines precise anatomical models for trainees, recommending they practice incisions on gourds and fruit before progressing to cadavers and live patients, an approach mirroring modern surgical education. The detail in these ancient texts reveals an intimate knowledge of human anatomy that defies historical assumptions. Sushruta documented over 120 surgical instruments, including scalpels resembling modern tenotomy knives for eye surgery and retractors that wouldn't look out of place in today's operating theaters. His description of cataract surgery, where a curved needle dislodges the clouded lens by entering the eye's edge, was still being performed with nearly identical tools in rural India well into the 20th century. Even more remarkably, the text describes skin grafts for nasal reconstruction using flaps from the cheek or forehead, complete with instructions to keep the transplanted tissue connected to its blood supply during healing, a principle plastic surgeons call the pedicle technique that wasn't formally recognized in the West until World War I. How did Ayurvedic surgeons achieve such precision without microscopes or germ theory? Part of the answer lies in their observational rigor. Dissection wasn't taboo in ancient India as it was in Europe. Students studied corpses preserved in flowing water to soften tissues, documenting structures down to individual ligaments and nerve pathways. The texts also reveal an empirical understanding of antisepsis boiling instruments, using herbal pastes to prevent infection, and even fumigating operating spaces with aromatic resins. While they couldn't see microbes, they recognized patterns of contamination centuries before Pasteur. The real mystery is why this knowledge remained isolated. While Europe struggled through the Dark Ages, Ayurvedic hospitals flourished with dedicated surgical wards and specialized tools. Some scholars believe climate played a role. India's tropical environment provided year-round access to medicinal plants for anesthesia and wound care, enabling surgical traditions to develop continuously. Others point to cultural factors. Surgery was considered a noble profession in ancient India, while many European surgeons until the Renaissance were barbers doubling as tooth pullers. Modern medicine is only beginning to validate these ancient practices. Research shows turmeric, used in Ayurvedic wound dressings, has potent anti-inflammatory properties, while the frankincense described for fumigation contains boswellic acids that inhibit infection. Perhaps most astonishing is the continued use of couching for cataracts in remote areas, proof that some techniques were so effective they persisted millennia beyond their origins. These texts force us to reconsider the timeline of medical progress. When a 16th century European traveler witnessed Indian rhinoplasty, a technique where surgeons fashioned new noses from forehead skin, they dismissed it as magic. Yet here was a system that mapped the human body with startling accuracy, developed specialized tools for specific procedures, and recorded outcomes with statistical precision, all while Hippocrates was still theorizing about bodily humors. The gap between ancient and modern medicine suddenly seems far narrower, bridged by threads of knowledge we're only now recognizing as centuries ahead of their time. In the year 138 AD, the imperial court of China's Han Dynasty witnessed something unprecedented. A bronze vessel shaped like a wine jar suddenly came to life. One of 8 dragon heads encircling its rim released a metal ball into the waiting mouth of a bronze toad below. According to court historians, this event signaled an earthquake that had just struck 400 miles to the west, days before messengers could arrive with news of the devastation. This was Zhang Heng's seismoscope, a device so advanced it wouldn't have an equal until the 19th century. The genius of this invention lay in its elegant simplicity. Inside the ornate vessel hung a delicate pendulum that would sway with distant tremors, unseen by human eyes. But here's where ancient Chinese engineering surpassed mere observation. The pendulum's movement triggered a series of levers that directed a single ball to fall through one of 8 dragon-headed tubes, each corresponding to a cardinal direction. When multiple balls dropped, officials could triangulate the quake's epicenter. Modern recreations prove the mechanism worked with startling accuracy, detecting quakes too faint for humans to feel yet hundreds of miles away. What baffles historians isn't just the device's precision, but the conceptual leap it represents. Zhang Heng lived in an era when earthquakes were commonly attributed to divine wrath or mythical creatures stirring underground. Yet his seismoscope treated seismic waves as measurable physical phenomena, an idea Europe wouldn't embrace until the 1800s. Some scholars believe he may have recognized P waves, the fast-moving primary waves that precede an earthquake's destructive S waves, allowing his device to predict tremors before they were felt locally. The real mystery is how this knowledge vanished. While later Chinese dynasties recorded earthquakes meticulously, the seismoscope's inner workings were either lost or deliberately kept secret. Only a handful of written descriptions survive, leaving modern engineers to puzzle over its exact mechanism. Some theories suggest it used an inverted pendulum suspended in liquid mercury, a concept similar to modern seismometers, while others propose a system of weighted arms that would dislodge balls when disturbed. Zhang Heng's invention forces us to reconsider the origins of scientific instrumentation. 17 centuries before the Richter scale, Here was a device that didn't just detect earthquakes but quantified their direction and relative strength. Its existence hints at a sophisticated tradition of mechanical engineering in ancient China, one that may have produced other lost technologies we've yet to rediscover. Perhaps most remarkably, the seismoscope reflects a world view where natural phenomena were neither magical nor random, but governed by principles waiting to be measured. In an age without textbooks or international collaboration, Zhang Heng's bronze dragons whispered a truth it would take the rest of the world millennia to hear, that the Earth itself has a language and humanity need only build the right tools to listen. Deep in the jungles of Central America, where the Milky Way blazes brighter than any city light, the Maya built temples that doubled as celestial calculators. Without lenses or brass instruments, they tracked the cosmos with such precision that their solar calendar was more accurate than Europe's until the Gregorian reform in 1582. While medieval astronomers struggled with flawed calculations, Mayan scribes recorded Venus's cycles with an error margin of just 2 hours over 584 days, a feat requiring observations spanning generations. Their secret wasn't advanced optics, but an obsessive dedication to patterns etched in bark paper codices and stone monuments, where celestial events aligned with sacred architecture down to the minute. The Dresden Codex, a surviving Mayan manuscript, reveals the sophistication of their astronomical methods. Pages filled with intricate tables chart not just Venus, but Mars, Jupiter, and solar eclipses centuries into the future. One section predicts a lunar eclipse in 1991, 1,300 years after the Codex was likely written, with an error of less than a day. How did they achieve this? The Maya treated time as a mathematical fabric, weaving together overlapping cycles like the 260-day sacred Tzolk'in and the 365-day Hob into a grand unified calendar called the Long Count. By cross-referencing these cycles with celestial events, they detected recurring patterns invisible to casual observers. Their observatories were the very cities they inhabited. At Chichen Itzá, the pyramid of Kukulkan casts a shadow during equinoxes that slithers like a serpent down its steps, a deliberate alignment proving they understood Earth's axial tilt. In Capan, a temple doorway frames Venus at its northernmost rise, while Palin's palace tower served as a sightline for tracking Jupiter's retrograde motion. These weren't passive observations. The Maya actively used architecture as a giant celestial compass, embedding astronomical knowledge into stone. What's most astonishing is their grasp of cosmic timescales. The Long Count calendar's base unit was the Baktan, 144,000 days, and inscriptions reference dates millions of years in the past and future. This long-term perspective allowed them to recognize phenomena like the slight discrepancy in Earth's orbit that causes the tropical year to be about 11 minutes shorter than the sidereal year, a nuance European calendars didn't account for until the Renaissance. The tragedy lies in what was lost. Spanish bishops burned thousands of codices as pagan works, leaving only 4 surviving astronomical texts. Modern scholars have had to reconstruct Mayan astronomy from carved stelae and the oral traditions of descendant communities. Yet even these fragments reveal a civilization that didn't just observe the heavens, but conversed with them, turning celestial mechanics into poetry written in numbers and stone. Their legacy whispers a provocative idea that brilliance isn't measured by technology alone, but by the patience to watch the sky until it reveals its secrets. Among all the mysteries of the ancient world, few are as visually striking as the Great Pyramid of Giza's near-perfect alignment to true north. Its 4 base edges deviate from cardinal directions by an average of just 3.5 arcminutes, less than 1/15 of a degree. To put that in perspective, Even some modern skyscrapers using laser-guided surveying equipment show greater discrepancies. The pyramid's north-south axis runs straighter than Paris's meridian line, established in the 17th century with advanced telescopes. This isn't just impressive engineering, it's a mathematical puzzle carved in limestone, raising profound questions about how Bronze Age architects achieved such precision without magnetic compasses, which wouldn't appear for another 2,000 years. The conventional explanation points to stellar observations using stars like Polaris or the circumpolar constellations to determine north. But here's the complication. Earth's axial wobble means Polaris wasn't the North Star in 2500 BC when the pyramids were built. Instead, researchers propose the builders might have used a method called the simultaneous transit technique, observing two stars circling the celestial pole. When these stars appeared vertically aligned in the night sky, their midpoint would indicate true north with remarkable accuracy. This method could theoretically achieve the pyramid's precision, but it requires painstaking observations over many nights and leaves no margin for error when scaling up to a 480-foot-wide base. Even more intriguing are the physical tools that might have made this possible. Some Egyptologists suggest the mysterious merkit, a palm rib device mentioned in texts, functioned as an astronomical alidade for tracking stars. Others point to the Bay-Enemi Anut, literally instrument of knowing, described in tomb paintings as a notched rod used with a plumb line. Recent experiments show these simple tools, combined with reflective pools of water as artificial horizons, could achieve alignment within the pyramid's margin of error. But these are educated guesses. No surviving manuals or diagrams explain the exact methods. The pyramid's corners add another layer of mystery. Not only are they aligned to cardinal directions, but their near-perfect 90-degree angles suggest the Egyptians possessed advanced geometric knowledge. The southeast corner deviates from a perfect right angle by just 12 arcseconds, about the width of a human hair seen from 10 feet away. This implies they understood principles like the 3-4-5 triangle method or circle segmentation centuries before Greek mathematicians formalized geometry. Some researchers speculate they might have used rope stretchers to create precise right angles, while others propose shadow tracking methods tied to the solar cycle. What makes this alignment truly enigmatic is its consistency across multiple pyramids. The Red Pyramid at Dosha and Khafre's Pyramid at Giza show similarly precise orientations, suggesting standardized techniques passed down through generations of builders. This wasn't a lucky accident, it was a repeatable system of astronomical surveying that modern engineers struggle to replicate with primitive tools. The methods may have been so ingrained in Egyptian culture that scribes saw no need to document them, much like master chefs might not write down techniques they consider basic knowledge. Recent technological discoveries add fuel to the mystery. In 2018, the Scan Pyramids project using muon radiography detected unexplained voids and density variations within the Great Pyramid features that some speculate could relate to alignment mechanisms. Could there be embedded architectural clues we've overlooked? The absence of written records forces us to read the stones themselves like a cryptic manual, where every casing block and corridor might hold fragments of lost knowledge. This precision wasn't just about vanity, it was cosmologically significant. Aligning structures with celestial forces reflected the Egyptian belief in maintaining cosmic order, or MAT. The pyramids weren't just tombs but monumental instruments connecting Earth to the heavens, their perfect angles mirroring the rays of the sun god Ra. In a civilization where astronomy, religion, and architecture were inseparable, the builders might have achieved their accuracy through a fusion of spiritual discipline and empirical observation that modern science struggles to categorize. The Great Pyramid's silent perfection stands as a testament to what's possible when human ingenuity merges with patient observation. Its stones whisper a challenge across millennia that true north might be found not just in the stars, but in the unwavering pursuit of precision, a lesson modern builders are still learning from their ancient counterparts. On storm-lashed Viking longships, where cloud and fog could obscure the sun for days, Norse sailors allegedly held a secret weapon, a translucent crystal they called a solarstein, or sunstone. Medieval sagas described navigators using these stones to locate the sun's position, even when the sky was completely overcast, a claim that seemed like poetic exaggeration until 2011. That's when a team of European physicists proved certain crystals like Iceland spar, a form of calcite common in Scandinavia, could indeed pinpoint the sun's location with 99.7% accuracy, even after sunset or during twilight. This wasn't mysticism but advanced polarization optics, a principle modern airplanes use in their cockpit instruments. The science behind sunstones is as elegant as it is ingenious. When light passes through calcite's crystalline structure, it splits into two beams, a phenomenon called birefringence. By rotating the stone until these beams appear equally bright, a navigator can determine the sun's azimuth relative to Earth's polarized light patterns. Researchers testing this method with replica Viking ships found it worked even in thick cloud cover or when the sun was 6 degrees below the horizon, conditions where human eyes see only uniform gray. What's more, combining the sunstone with a simple wooden shadow board, like those found in archaeological sites, could provide course corrections accurate to within 1 degree. Evidence for their use goes beyond legend. A 16th-century shipwreck near Alderney in the English Channel yielded an Iceland spar crystal near navigational tools, its surfaces worn smooth from handling. Viking trade routes also aligned suspiciously well with deposits of optical quality calcite in Iceland and Norway, suggesting these minerals were deliberately sourced. Even the sagas contain practical details. One describes holding the stone overhead and marking where light spots converge on its surface, matching modern experimental methods. This technology's sophistication becomes clear when compared to contemporary navigation. While medieval European sailors relied on coastal landmarks or crude magnetic compasses prone to deviation, Viking sunstones provided celestial accuracy independent of weather or proximity to shore. Some researchers believe they might explain how Norse explorers reached North America centuries before Columbus, navigating the featureless North Atlantic with tools no thicker than a thumb. The disappearance of sunstone navigation remains puzzling. As magnetic compasses spread through Europe in the 13th century, references to the crystals fade from records. Perhaps their dependence on clear skies at dawn and dusk made them less reliable than all-weather compasses, or maybe the knowledge was kept secret by elite navigators. What's certain is that this forgotten tool represents more than a clever trick. It's a window into how the Vikings viewed the natural world. Where others saw obstacles, they saw patterns invisible to the naked eye, turning sunlight's hidden fingerprints into a roadmap across oceans. In an age before satellites, their crystals whispered directions written in light itself. Buried beneath the sands of Mesopotamia for nearly 2 millennia, a cluster of unassuming clay jars might hold the key to one of archaeology's most electrifying mysteries. Discovered in 1936 near Baghdad, these peculiar artifacts, each no larger than a fist, contained an iron rod encased in a copper cylinder, sealed with asphalt and traces of acidic residue. To German archaeologist Wilhelm Koenig, their design seemed suspiciously deliberate. When filled with vinegar or citrus juice, the jars could produce a measurable electric current. If his theory holds, these so-called Baghdad batteries predate Alessandro Volta's official invention of the battery in 1800 by over 1600 years, a claim that rewrites the history of technology. Recreations prove the jars could generate around 1 volt of electricity, enough to produce a mild tingling sensation or enable simple electroplating. Modern experimenters have used replicas to gild silver objects with gold leaf, demonstrating how ancient artisans might have employed these devices for decorative metallurgy. The acidic electrolyte, possibly wine or fermented grape juice, would have corroded the iron rod, releasing electrons that flowed through the copper outer shell. While the power output was modest, connecting multiple jars in series could have achieved higher voltages, hinting at a more sophisticated understanding of electrical principles than previously imagined. What's most compelling isn't just the batteries themselves, but the context of their discovery. Found among ritual objects in a Parthian-era village, their purpose remains enigmatic. Some scholars suggest they powered electrotherapy for pain relief, noting ancient Greek and Roman texts describing how electric fish were used to treat headaches. Others propose they illuminated religious statues with flickering gold plating to simulate divine radiance, a tantalizing parallel to the ever-burning lamps mentioned in Mesopotamian and Egyptian temple records. The most controversial theory posits they were components of a larger, lost technology, perhaps used in conjunction with Leyden jar-like capacitors described in later Arabic manuscripts. Skeptics argue the jars might have been mundane storage containers, their battery function coincidental, yet the asphalt seals an excellent insulator, and the precise placement of dissimilar metals suggest intentional design. Even more intriguing are surviving accounts from the same period describing magical phenomena that align with electrical effects. 1st century Roman author Pliny the Elder wrote of gold refiners using earthenware vessels to manipulate metals in ways modern chemists recognize as electrolysis. Could this be a fragmented record of widespread ancient electrochemistry? The Baghdad batteries force us to reconsider the boundaries of ancient innovation. In a world without textbooks or standardized science, empirical discovery might have flourished in isolated pockets, knowledge passed hands-on from artisan to apprentice until wars or cultural shifts erased it. These humble jars whisper a provocative possibility that our ancestors' understanding of nature's forces wasn't just philosophical but startlingly practical. Whether they powered forgotten medical devices, religious spectacles, or workshops full of gleaming electroplated treasures, their very existence sparks a larger question: how many other ancient miracles might have been the products of deliberate, if unrecorded, electrical experimentation? Across the vast, trackless deserts of Australia, where European explorers once perished from thirst and disorientation, indigenous communities traversed thousands of miles with nothing but the stars overhead and songs in their hearts. These weren't just melodies, they were living maps, intricate navigational systems called songlines that encoded the entire continent's topography into rhythm and verse. Each landmark, waterhole, and seasonal pathway was memorized through lyrics describing the creator-ancestors' journeys during the dreamtime, turning oral tradition into an astonishingly precise geographic database. Modern anthropologists comparing these songs to satellite maps have found them accurate to within meters across distances exceeding the length of Europe, a feat of memory and observation that challenges our reliance on digital navigation. The genius of songlines lies in their multidimensionality. A single verse might describe the shape of a mountain range, the scent of plants indicating underground water, and the position of constellations during harvest season, all woven into a narrative that could be walked, sung, or painted in sand. Unlike Western maps that flatten landscapes into 2 dimensions, songlines preserved knowledge vertically, noting celestial markers for night travel and seasonal cues like flowering patterns or animal migrations. In Arnhem Land, elders demonstrated how certain melodies correspond to the pitch and rhythm of footfalls across specific terrains, creating an almost musical topography where the land itself became a score to be performed. What baffles modern researchers is the sheer scale of this mental cartography. The Yolngu people's songlines, for example, stretch over 900 miles from northern Australia's coast to the central desert, with each clan responsible for memorizing their segment like stations on a celestial subway. When tribes gathered for ceremonies, these fragments would connect into continent-spanning routes, passed down unchanged for millennia. Neuroimaging studies suggest such feats of memory activate both auditory and spatial cognition centers simultaneously, a mental GPS encoded in song. The comparison to modern technology is revealing. Where GPS gives coordinates but no context, songlines embedded survival knowledge, which plants were medicinal, where game congregated in drought years, how to read cloud formations predicting rain. They also served as legal documents, encoding territorial boundaries and resource rights within their verses. This wasn't just navigation, it was an entire governance system sung into existence. The fragility of this knowledge became tragically apparent during colonial disruption, with elders unable to pass down songs due to forced relocations. Some songlines fractured like interrupted transmissions. Yet in communities where the tradition persists, like the Pitjantjatjara lands, young people still learn to navigate hundreds of miles without maps by singing the country into being. Scientists now collaborate with elders to document these songs, revealing subtle cues like verses referencing magnetic termite mounds that consistently align north-south, that may have functioned as natural compasses. Songlines force us to reconsider what we've lost in the shift from oral to digital culture. In an age where phones tell us where to turn but not why a place matters, these melodic maps remind us that navigation was once a sacred act, a dialogue between memory, landscape, and the stars. They whisper an uncomfortable truth that some wisdoms can't be downloaded, only earned through generations of careful listening to the Earth's enduring song. In the scorching deserts of Iran, where summer temperatures routinely climb above 120 degrees, ancient architects devised a cooling system so effective that modern engineers still study it in awe. Persian windcatchers, or badgers, rise like square chimneys above centuries-old cities, harnessing the slightest breeze to transform sweltering interiors into oases of comfort, all without a single watt of electricity. These ingenious structures work on principles so refined that contemporary tests show they can lower indoor temperatures by up to 20 degrees, rivaling the performance of energy-guzzling air conditioners. The secret lies in their precise orientation to prevailing winds, combined with subterranean water channels called qanats that add evaporative cooling. As hot air enters the tower's windward openings, it's funneled downward through clay-cooled shafts, while rising warm air escapes through opposite vents, creating a continuous circulation that some desert dwellers still prefer over modern cooling systems. The sophistication of these passive designs becomes clear when examining their variations across regions. In Yazd, the desert capital of Iran, windcatchers feature multiple directional openings to catch breezes from any angle, while coastal versions in the Persian Gulf incorporate moist seaweed to enhance cooling. Some towers even include adjustable internal dampers to regulate airflow, a Bronze Age precursor to today's smart thermostats. What's truly remarkable is how these structures integrate with broader urban planning. Cities like Bam arranged entire neighborhoods around windcatcher alignments, creating microclimates where the collective downdraft from dozens of towers generated a natural, cooling grid. Underground ice houses, another Persian innovation, used windcatcher airflow to preserve winter ice through summer months, an ancient solution to food storage that required zero energy input. Yet the real mystery isn't how windcatchers worked, but why this sustainable technology faded from widespread use. The decline began with 20th century urbanization and the influx of cheap fossil fuels, as concrete high-rises replaced traditional mud brick homes better suited to passive cooling. Modern electrical grids made brute force air conditioning seem simpler than maintaining ancient architectural knowledge, even as it increased energy demands. Some scholars point to cultural shifts that devalued vernacular architecture, while others note that Qanat systems, the lifeblood of windcatchers, required communal maintenance that broke down with rural migration. The irony is painful. A technology perfected over millennia was abandoned just as climate change made its benefits most relevant. Today, a quiet revival is underway. Architects from Dubai to Arizona are adapting windcatcher principles for contemporary buildings, combining them with solar panels and thermal mass materials. In Tehran's Pardes Technology Park, a modernized Badger system cuts cooling energy use by 70%, proving ancient solutions can complement modern engineering. Even more promising are hybrid designs that merge windcatcher airflow with geothermal pipes, creating systems that work in humid climates where traditional versions struggled. The legacy of Persian windcatchers challenges our assumptions about progress. In an era obsessed with high-tech solutions to climate change, these towers whisper an alternative, that sometimes the most advanced technology isn't the newest but the wisest. They stand as monuments to a time when humanity worked with nature's rhythms rather than against them, a lesson written in brick and breeze that grows more urgent with each record-breaking heatwave. Unearthed in 1908 amid the ruins of Crete's Minoan palace of Feistos, this palm-sized clay disc remains one of archaeology's most tantalizing enigmas. Covered on both sides with 45 distinct symbols stamped in a precise spiral, the Feistos Disk doesn't just defy translation, it stands utterly alone. Unlike Linear A or B, the other undeciphered scripts of Bronze Age Crete, this artifact's symbols weren't hand-carved but pressed into the clay with pre-made seals, making it the earliest known example of movable type printing in history, a technology that wouldn't reappear for another 3,000 years. What's immediately striking is the disk's visual rhythm. The spiraling symbols, human figures, birds, shields, and geometric shapes are grouped into discrete words separated by slashes, suggesting a structured language rather than random decoration. Yet despite over a century of study by linguists, cryptographers, and even artificial intelligence, no one has convincingly matched these symbols to any known script. Some researchers detect similarities to Anatolian hieroglyphs or early Cypriot syllabaries, while others argue the symbols represent a completely isolated writing system, possibly a ceremonial cipher known only to Minoan priests. The disk's physical context adds another layer of mystery found in a temple complex alongside ritual objects, yet with no duplicates or related artifacts ever discovered. Attempts to decipher it have veered from the scholarly to the fantastical. One controversial theory proposes the symbols encode a hymn to the Minoan mother goddess, while another interprets them as an ancient board game's instructions. Computer analysis in 2014 revealed statistical patterns resembling natural language, but without a bilingual key like the Rosetta Stone, progress stalls. The most promising clue might lie in the numbering system, groups of dots beside certain symbols that could represent a lunar calendar tracking rituals or agricultural cycles. The disk's craftsmanship raises equally profound questions. Each symbol was stamped with remarkable consistency, implying the existence of a standardized set of reusable type, a concept thought to be invented in medieval China. Why wasn't this technique adopted for administrative records or expanded upon? Some speculate it was a sacred technology restricted to religious elites, while others suggest it was an experimental dead end, like a Bronze Age prototype abandoned before reaching its potential. Modern technology has only deepened the puzzle. High-resolution scans confirm the disk was fired intentionally, not accidentally burned, hinting at deliberate preservation. Yet thermoluminescence testing reveals an oddity: the clay's composition differs slightly from local Feistos soil, suggesting it might be an import or even a forgery, though most experts dismiss this due to its stratigraphic context. What makes the Feistos Disk uniquely haunting isn't just its indecipherability, but what it represents: a fleeting glimpse of a knowledge system that flourished and vanished without leaving descendants. In its spiral, we see the ghost of a thought process, a way of organizing information that modern minds can recognize but not reconstruct. It whispers a humbling truth that not all codes are meant to be broken, and some ancient voices may remain forever just beyond our understanding. In the bustling libraries of 11th century Cairo, a scholar named Ibn Al-Hazen, known in the West as Al-Hazen, conducted experiments that would shatter ancient misconceptions about vision. While Europe still clung to the Greek idea that eyes emitted rays to see objects, Al-Hazen proved light actually enters the eye rather than leaving it. His seminal work, The Book of Optics, didn't just correct this centuries-old error. It laid the mathematical foundations for everything from eyeglasses to space telescopes, blending rigorous experimentation with precise geometry in a way that wouldn't become standard in Europe until Galileo's time. Al-Hazen's breakthroughs went far beyond theoretical musings. He designed the first camera obscura, demonstrating how light travels in straight lines by projecting images through a pinhole, a principle all modern cameras rely on. His studies of refraction explained why objects appear bent in water, complete with diagrams calculating angle deviations that match modern physics equations. Perhaps most astonishing were his investigations into the anatomy of the eye, where he correctly identified the cornea and lens as light-focusing elements centuries before Renaissance anatomists. These weren't guesses. Al-Hazen tested each hypothesis with controlled experiments, often building specialized apparatus like darkened chambers and adjustable light sources to isolate variables, a methodological rigor that wouldn't resurface until the scientific revolution. The real puzzle isn't how Al-Hazen achieved these insights, but why they remained confined to the Islamic world for so long. The Book of Optics circulated widely from Cordoba to Samarkand, influencing Persian astronomers who used its principles to build precision observatories. Yet when medieval Europe finally encountered these ideas, it was often through fragmented Latin translations filtered through layers of interpretation. Some historians point to the collapse of the Abbasid Caliphate and the Mongol invasions as disruptors of scholarly networks, while others note that European universities initially prioritized Aristotle's outdated theories over empirical Arabic texts. The delay had profound consequences. Had Al-Hazen's work reached Roger Bacon or Kepler earlier, the telescope might have appeared 2 centuries before Galileo. What's often overlooked is how deeply Islamic optics intertwined with other disciplines. Mathematicians like Al-Kindi used optical principles to develop cryptography, while physicians applied them to correct vision disorders with early lenses. The same wave theory that explained rainbows in Al-Hazen's treatises also informed intricate mosque designs, where strategically placed windows created celestial light patterns tracking prayer times. This wasn't isolated genius, but part of an entire ecosystem of inquiry where opticians, architects, and astronomers cross-pollinated ideas. Modern science is still catching up to some of these insights. Researchers recently confirmed Al-Hazen's observations about how the brain interprets inverted retinal images, a process he deduced through painstaking experimentation rather than dissection. His descriptions of afterimages and color adaptation now underpin our understanding of visual perception. Even his errors proved fruitful. His attempts to mathematically model the atmosphere's effect on twilight led to the discovery of Earth's mesosphere. The legacy of medieval Arabic optics forces us to reconsider the geography of scientific progress. In a Basra prison cell, where Al-Hazen was briefly confined after failing to regulate the Nile's floods, one man's studies of light beams illuminated truths that would take the rest of the world half a millennium to independently rediscover. His work whispers an uncomfortable truth, that knowledge moves not in straight lines but through refractions of history, bending and dispersing until it finally comes into focus. Buried in Viking graves across Europe, a handful of swords bear a name that struck terror into medieval hearts: Ulfbert. These weapons weren't just feared for their wielder's brutality, but for their almost supernatural quality. While most European swords of the 9th to 11th centuries were brittle iron prone to snapping in battle, Ulfbert blades flexed and held razor-sharp edges, their distinctive inscription glowing faintly along the fuller. Modern metallurgical analysis reveals why they were forged from crucible steel with a carbon content near 1.2%, a purity unmatched until the Industrial Revolution. This wasn't just superior craftsmanship, it represented a material science leap that historians still struggle to explain. The secret lay in the steel's origin. Unlike the slag-riddled iron Europeans produced in bloomery furnaces, Ulfbert steel contained almost no impurities. Its microstructure shows the telltale signs of high-temperature crucible smelting, a technique thought to have existed only in Central Asia at the time. Chemical fingerprints point to ore sources in modern-day Afghanistan, suggesting these swords were made from imported ingots of so-called ceramic steel, traded along routes stretching thousands of miles. How this material reached Viking smiths remains one of archaeology's great riddles. Some scholars propose it traveled north via ruse merchants along the Volga trade routes, while others note Arabic accounts describing Norse traders in Baghdad's markets, possibly exchanging amber and furs for ingots. What's truly baffling is the technical knowledge required to work this steel. Crucible steel melts at nearly 3,000 degrees Fahrenheit, temperatures Viking furnaces supposedly couldn't reach. Yet Ulfbert Smith somehow mastered the precise forging methods needed to prevent the high-carbon steel from becoming brittle. Recent experiments show they may have used layered construction, sandwiching the crucible steel between softer iron to absorb shock while maintaining edge hardness. The blades also exhibit sophisticated pattern welding, with alternating bands of steel creating microscopic serrations that enhanced cutting ability, a technique Japanese swordsmiths wouldn't perfect until centuries later. The disappearance of this technology is as mysterious as its origins. After the 12th century, no new Ulfbert swords appear, and European steel quality regressed for hundreds of years. Climate studies suggest a possible clue: the medieval warm period that had opened Arctic trade routes ended around 1300, possibly disrupting the supply chain. Others theorize that the Khwarezmian Empire's collapse severed Central Asian trade networks, cutting off the steel source. Whatever the cause, the loss was so complete that when Renaissance metallurgists tried recreating similar weapons, they assumed the Norse had used magic. These swords shatter stereotypes about Viking technology. Far from the crude barbarians of popular imagination, Ulfbert Smiths were material scientists operating at the cutting edge, quite literally, of their era's metallurgy. Their legacy lingers not just in museum cases, but in the enduring human quest to transform raw elements into objects of both beauty and deadly precision. In their gleaming surfaces, we see reflections of a forgotten globalization where Afghan mines, Eurasian trade routes, and Scandinavian workshops connected to produce artifacts that still defy easy explanation. Hidden within ancient Sanskrit texts like the Mahabharata and the Vaimanika Shastra lie descriptions that read less like mythology and more like aerospace engineering manuals. Vimanas, often translated as flying chariots, are depicted not as fantastical divine vehicles, but as sophisticated machines with detailed technical specifications. Some passages describe multi-tiered craft powered by rotating mercury vortex engines, equipped with protective metal plating and weapons capable of projecting beams of light. The Samarangana Sutradhara, an 11th century text, dedicates an entire chapter to Vimana construction, discussing materials selection, pilot training, and even aerial navigation techniques that include avoiding storms and calculating altitude. These aren't vague poetic metaphors, they're shockingly precise accounts that mirror modern aeronautical principles. The controversy lies in interpreting these descriptions. Skeptics argue that Vimanas are purely symbolic, representing spiritual ascension rather than physical flight. Yet the texts contain startlingly practical details, like instructions for insulating pilots against high-speed travel or stabilizing crafts using liquid mercury gyroscopes. In 1923, a Sanskrit scholar named G.R. Josiah claimed to have translated texts describing Vimana propulsion systems powered by solar absorption plates and mercury engines, sparking debates about whether these could represent lost energy technologies. While mainstream archaeology dismisses these as later inventions or allegories, the specificity raises eyebrows. One passage warns against flying certain Vimanas over forests, as their propulsion could ignite the trees, an odd precaution if the vehicles were merely mythological. Modern attempts to reconcile these accounts point to several possibilities. Some researchers suggest Vimana descriptions might preserve garbled memories of advanced siege engines or hot air balloons, while others note similarities between mercury vortex systems and modern ion propulsion concepts. The most tantalizing theory involves the mythical 9 Unknown Men, a secret society supposedly entrusted by Emperor Ashoka in the 3rd century BC with guarding advanced scientific knowledge. Could Vimana texts be fragments of this protected wisdom, later misunderstood as divine lore? The archaeological record offers no physical evidence of ancient aircraft, but intriguing parallels exist. The Shakuna Vimana is described as bird-shaped with hinged wings, a design resembling 19th century ornithopters. More provocatively, a 4,500-year-old Mesopotamian seal depicts a temple atop a multi-stage rocket-like structure, while Egyptian hieroglyphs in the Temple of Seti show what appear to be helicopter and submarine shapes. These anomalies don't prove ancient flight, but they hint at cross-cultural motifs that defy easy explanation. What makes Vimanas uniquely challenging is their blending of the plausible and the impossible. Descriptions of aerial battles in the Mahabharata, complete with projectile weapons and radiation-like effects, read disturbingly like modern warfare. Yet the same texts claim some Vimanas could become invisible or travel between dimensions, clearly fantastical elements. This duality forces us to confront how ancient cultures might have recorded advanced technology through the lens of their understanding. Could rotating mercury engines describe actual propulsion systems, while invisibility represents stealth technology misinterpreted by later scribes? The Vimana texts ultimately serve as a Rorschach test for our assumptions about antiquity. Whether they preserve fragments of lost engineering or represent humanity's timeless fascination with flight, they underscore how thin the line between myth and memory can be. In their cryptic verses, we glimpse the shadow of a disturbing possibility that our ancestors might have soared skies we still struggle to conquer, leaving only enigmatic texts as their contrails. On a remote island where towering stone heads gaze eternally toward the horizon, another mystery lies hidden in plain sight. Dozens of wooden tablets covered in delicate, hieroglyph-like symbols that no living person can read. This is rongorongo, the enigmatic script of Easter Island, and it may represent the only indigenous writing system to emerge independently across the entire Pacific Ocean. Unlike the island's famous Moai statues, these inscribed artifacts don't reveal their secrets so easily. Carved in reverse boustrafeden, a zigzag pattern where lines alternate direction like an ox plowing a field, the glyphs depict everything from crouching human figures to crescent moons, frigate birds, and abstract geometric shapes. But are they sacred hymns, genealogical records, or something more profound? The answer died with the last scribes who understood them, leaving behind fragments of a knowledge system as isolated as the island itself. What makes rongorongo uniquely puzzling is its apparent sudden appearance. Linguistic evidence suggests Easter Island was settled around 1200 AD, yet the earliest surviving tablets date only to the 18th century, shortly after European contact. Some scholars argue this timing proves the script was inspired by Spanish writing, but the glyphs show no resemblance to Latin letters. Others note the sheer complexity of rongorongo, with over 600 distinct signs, including compound glyphs that may represent syllables or concepts, rules out spontaneous invention. This raises a haunting possibility that older tablets once existed, perhaps carved on now vanished palm wood, leaving the surviving fragments as echoes of a much deeper literary tradition. The tablet's physicality tells its own story. Most were crafted from toromero wood, a tree now extinct on the island, using obsidian flakes or shark teeth as carving tools. The glyphs themselves aren't merely scratched surfaces but precise grooves with raised edges, suggesting specialized tools and trained scribes. Some tablets show wear patterns indicating frequent handling, while others bear traces of red pigment, hinting at ceremonial use. The most intact specimen, the Santiago staff, measures over 2 feet long and contains over 2,000 glyphs, a density of information that implies sophisticated record-keeping. But records of what? Attempts at decipherment have followed false leads for generations. In the 1860s, a French missionary claimed local elders could read the tablets aloud, but their translations, purportedly creation myths, proved unreliable. Modern approaches range from statistical analysis linking glyph frequencies to Polynesian oral traditions, to controversial theories proposing the script encodes a lunar calendar or even numerical tax records. One tantalizing clue comes from glyph 28, which resembles the Polynesian symbol for kumara, sweet potato, a staple crop whose cultivation required precise seasonal tracking. Could rongorongo have been an agricultural almanac for surviving in one of Earth's most isolated ecosystems? The script's demise is as tragic as it is mysterious. After Peruvian slave raids in the 1860s decimated Easter Island's population, only a handful of rongorongo literate elders survived. By the time anthropologists arrived, the knowledge chain had broken. Today, just 26 authentic tablets remain, scattered in museums from Vienna to Washington, D.C., their surfaces darkened by age and the oils of countless frustrated researchers. Digital imaging has revealed previously invisible glyphs, and machine learning algorithms now search for patterns across thousands of symbols, yet progress inches forward at a glacial pace. Rongorongo's greatest lesson might be about fragility. In a world where writing systems like Egyptian hieroglyphs were deciphered through bilingual stones, this script stands alone, an intellectual island with no bridge to modern understanding. Its very existence contradicts assumptions that writing only arose in large hierarchical societies, proving that even small, isolated cultures could develop complex symbolic communication. As the waves of time slowly erode Easter Island's cliffs, Rongorongo endures as both a monument and a warning. That knowledge, no matter how meticulously carved, is only as permanent as those who preserve its meaning. Deep in the arid valleys of ancient Peru, the Moche civilization perfected a gleaming alchemy that would stump modern chemists for centuries. Between 100 and 800 AD, these master metallurgists developed a gold plating technique so advanced that 19th century scientists initially refused to believe it predated European electrochemistry. Using mercury as a conductive medium, they bonded microscopically thin layers of gold to copper artifacts through a process called electrochemical replacement plating, a method not formally documented in the West until 1805. The precision of their work still dazzles researchers today. Ceremonial masks and nose ornaments from royal tombs show flawless gilding with gold layers just 2 microns thick, achieving coverage so uniform it rivals modern industrial plating. What makes this technology revolutionary isn't just its early appearance, but the sophisticated understanding of chemistry it reveals. The Moche didn't merely mix gold and mercury, they controlled the reactions with startling precision. Analyses of gilded objects show they selectively applied heat to evaporate excess mercury without burning away the gold, leaving behind pure, lustrous surfaces. Some artifacts even display gradient plating, where gold thickness varies deliberately to create visual effects, indicating mastery over reaction rates and solution concentrations. This wasn't trial and error, it was systematic materials science developed without the theoretical frameworks of modern chemistry. The process began with naturally occurring mercury deposits, which the Moche mined from the nearby Santa Barbara quicksilver mines. They combined this with gold dust to create an amalgam, a paste that could be painted onto copper objects. When heated carefully, the mercury vaporized, leaving only the gold bonded to the surface. But here's the true brilliance. Residue analysis reveals they often added acidic fruit juices to the mixture, likely observing how these substances improved plating quality. Modern experiments confirm that weak organic acids like those in fermented pineapple juice accelerate the replacement reaction, proving the Moche's empirical methods had practical foundations. Why did this knowledge emerge in the Andes rather than elsewhere? The answer lies in the region's unique geology. Northern Peru sits atop one of Earth's richest mercury belts, with abundant cinnabar deposits that could be processed into liquid mercury. The Moche's access to both mercury and gold, another local resource, created ideal conditions for experimentation, but resources alone don't explain their innovation. Unlike contemporary European metalworkers who prized purity, the Moche embraced material interactions, valuing how metals behaved together over their individual properties. This conceptual breakthrough allowed them to see possibilities invisible to cultures obsessed with singular materials. The disappearance of this technology parallels the Moche's mysterious decline around 800 AD, but fragments survived through later cultures like the Quipu and Inca. Spanish chroniclers recorded indigenous goldsmiths using mercury-based techniques during the conquest, though the knowledge gradually faded under colonial rule. Today, archaeologists are piecing together the full scope of Andean metallurgy through unlikely clues, from the mercury vapors still detectable in ancient workshop floors to the faint golden sheen on corroded copper artifacts when viewed under electron microscopes. These discoveries shatter old narratives about technological progress. While Europe languished in the early Middle Ages, Andean metallurgists were conducting what amounted to nanoscale engineering, manipulating matter at levels invisible to the naked eye. Their legacy isn't just golden artifacts, but a radical idea. That innovation flourishes not along a single path, but through countless branching trails, some leading to futures only now coming into view. On crisp, moonless nights far from city lights, a faint, ethereal glow sometimes rises from the horizon, a triangular veil of radiance stretching along the zodiac constellations. Modern astronomy calls this the zodiacal light, sunlight reflecting off cosmic dust drifting through the inner solar system. What's astonishing isn't its existence, but how consistently ancient cultures documented this subtle phenomenon centuries before telescopes could confirm it. Babylonian clay tablets from 700 BC describe the glow that follows the sun's path, while Mayan codices reference a celestial serpent aligning with Venus's orbit. Chinese imperial astronomers meticulously recorded its appearances alongside comets and novas, noting its seasonal variations with an accuracy that matches NASA's satellite data. These weren't vague poetic references, they were systematic observations of a phenomenon so dim that most modern stargazers, accustomed to light-polluted skies, will never see it unaided. The mystery deepens when we consider the observational conditions required. Zodiacal light is approximately as bright as the Milky Way, but spread over a much larger area of sky, making its contrast against the darkness incredibly subtle. To detect it consistently, ancient astronomers would have needed not just exceptionally clear and dark skies, which many civilizations had, but also disciplined observation protocols to distinguish it from twilight glow or atmospheric haze. The Mayas' ability to document its 45-degree elongation from the sun suggests they used horizon markers or architectural alignments to quantify its position, while Greek accounts by Callisthenes describe how Egyptian priests timed its appearance relative to dawn and dusk to the minute. This level of precision implies more than casual stargazing. It points to dedicated observation platforms, possibly with darkened adaptation chambers to heighten night vision. What's even more intriguing are the techniques cultures developed to enhance their perception of faint celestial phenomena. Polynesian navigators spoke of lying in shallow reef pools to steady their gaze while observing low-contrast stars near the horizon, a method that coincidentally reduces eye strain and improves detection of diffuse light. Persian astronomers described using obsidian mirrors to shield their eyes from peripheral light pollution, effectively creating a primitive form of contrast enhancement. The Dogon people of Mali, renowned for their astronomical knowledge, practiced prolonged darkness immersion rituals lasting up to 3 days before important observations, a technique modern researchers confirm significantly improves sensitivity to faint light sources. These weren't just random practices but calibrated methods born from generations of accumulated experience. The disappearance of this observational acuity reveals how technology can atrophy human senses. As artificial lighting transformed night skies across civilizations, the need to develop extreme visual sensitivity faded. Today, digital sensors can detect zodiacal light effortlessly, but we've lost the cultural memory of how to see it with unaided eyes, a skill that once guided agricultural calendars and navigation across oceans. Recent experiments with vision-trained subjects show that after months of practice, some individuals can regain this ancestral ability, spotting zodiacal light under conditions matching ancient descriptions. Perhaps the most profound lesson lies in what these accounts suggest about lost scientific methodologies. Ancient astronomers didn't just observe, they engineered their perception, treating the human eye as a precision instrument to be calibrated and maintained. Their success in documenting phenomena like zodiacal light hints at entire systems of knowledge, methods for training vision, techniques for enhancing contrast, protocols for eliminating bias that were never written down, only passed through apprenticeship. In our age of digital sensors and augmented reality, these forgotten arts remind us that sometimes the most advanced technology is the neural circuitry between our ears and the patience to let it adapt to the universe's whispers. 2,000 years before seismographs dotted the globe, Chinese imperial officials kept watch for earthquakes using an unlikely early warning system, the agitated movements of rats and the sudden clouding of well water. The Haohanshu, a historical text from 5th century China, records how astronomer Zhang Heng's famous seismoscope wasn't the empire's only tool for anticipating tremors. Local magistrates maintained detailed logs of environmental anomalies, from frenzied snake migrations to fish leaping from ponds, recognizing these as nature's distress signals before the ground itself began to shake. Modern geologists have uncovered startling validation for these ancient methods. Studies of the 1975 Haicheng quake show animals in the region exhibited abnormal behavior weeks in advance, while satellite data now confirms groundwater chemistry shifts precede major seismic events by days or even weeks. The sophistication of China's seismic monitoring network becomes clear when examining surviving administrative records from the Tang dynasty. Provincial officials were required to submit quarterly Earth auspice reports documenting unusual animal activity, well levels, and even changes in vegetation patterns. One particularly meticulous 8th century log from Sichuan notes how a sudden die-off of bamboo forests preceded a major tremor by 37 days, a correlation modern ecologists attribute to subterranean gas releases affecting root systems. What's most impressive isn't just the observational rigor, but how this data informed practical disaster response. The Tiangong Kaiwu, a Ming Dynasty encyclopedia, describes evacuation protocols triggered by mass bird migrations or the appearance of earthquake clouds, streaky atmospheric formations now recognized as potential indicators of underground stress buildup. Contemporary science is only beginning to understand the mechanisms behind these ancient indicators. Researchers at Stanford have documented how stressed rock layers release charged particles that can affect animal behavior through chemical changes in groundwater, while Japanese studies show certain fish species detect electromagnetic disturbances preceding quakes. The most compelling validation comes from China's own 21st century earthquake weather stations, where automated cameras monitor livestock alongside seismometers, confirming that horses and cattle really do grow restless hours before minor tremors. This fusion of ancestral wisdom and modern instrumentation raises an unsettling question. Did bureaucratic upheavals during China's 19th century collapse fracture a predictive system that might have rivaled today's early warning networks? What modern disaster preparedness could learn from these methods isn't just about observing nature, but interpreting its interconnected signals. Where current seismic sensors provide minutes of warning at best, the Chinese tradition sought patterns across entire ecosystems, tracking how bird nests built unusually high one year might correlate with subsequent landslides, or how well water turning bitter often preceded aftershocks. This holistic approach, preserved in poems and provincial gazetteers rather than technical manuals, represents a lost science of environmental forecasting where every creature from ants to oxen served as living sensors in a vast organic detection grid. The most haunting evidence of this system's effectiveness lies in what didn't happen: the absence of major quake-related death tolls in certain well-documented periods despite China's intense seismic activity. Imperial records from 780 AD show meticulous preparations in the weeks before a catastrophic Shaanxi earthquake, including grain stockpiling and reinforced buildings in provinces where officials had noted 3 successive nights of sleepless dogs. While modern seismology excels at measuring quakes as they occur, these fragments of ecological seismology whisper an uncomfortable truth: that our ancestors may have glimpsed a predictive art we're only now rediscovering through satellite arrays and machine learning. In their careful watching of nature's subtle unrest, they developed a language of the earth we've only begun to relearn. From self-healing concrete to earthquake predictors, these 22 lost knowledge systems force us to confront a humbling truth: human brilliance isn't confined to any single era or civilization. Each discovery peels back layers of historical assumption, revealing how ancient innovators solved problems we're still grappling with today. The Roman concrete that repairs its own cracks could transform our crumbling infrastructure. The Damascus steel with its mysterious nanostructure might inspire unbreakable alloys, and the ecological seismology of ancient China, where officials read the land's subtle warnings, could revolutionize how we prepare for natural disasters. What's most striking isn't just the sophistication of these technologies, but the different paths they took to get there. While modern science often relies on theoretical frameworks and lab experiments, many ancient breakthroughs emerged from generations of hands-on observation. Persian architects didn't calculate fluid dynamics to design windcatchers; they felt the breeze behavior across centuries and shaped stone to meet it. Ayurvedic surgeons didn't need microscopes to map human anatomy. They learned it through ritual dissections and meticulous record-keeping. These weren't primitive guesses, but refined systems of knowledge built through patient engagement with the material world. The disappearance of these systems carries urgent lessons. Some were lost to conquest, like the Inca quipus burned by Spanish priests. Others faded when centralized societies collapsed, taking their supply chains and specialized labor pools with them. A few may have been deliberately suppressed, like the Byzantine Empire's lethal Greek fire formula. But the common thread is fragility: how easily the threads of knowledge can unravel when cultures fracture or priorities shift. In an age where we take information permanence for granted, these gaps remind us that no technology, no matter how advanced, survives without deliberate stewardship. Yet hope lingers in the cracks between what we've lost and what we might recover. Modern scientists now study Roman concrete with electron microscopes, decode Quipu patterns with AI, and test Viking sunstones in replicated voyages. Sometimes the past offers not just inspiration, but ready-made solutions if we're willing to look without prejudice. That Baghdad Battery on a museum shelf might hold clues to sustainable energy storage. Those songlines echoing in Australian deserts could reshape how we navigate a post-GPS world. The irony is poignant. The very technologies we consider cutting-edge often have roots stretching back millennia. As the video ends, consider this: the next great leap forward might not come from some futuristic lab, but from a careful rereading of texts we dismissed as myth or a fresh analysis of artifacts gathering dust in storage. The Maya tracked Venus cycles with unerring precision using nothing but numbered sticks and stone observatories. What else might they, and all these other cultures, have known that we're only beginning to comprehend? The comments await your theories, and the next episode will delve even deeper into history's untold innovations. Until then, keep questioning, because every answer from the past reshapes